do some problems involving gravity, right? So gravity and Newton's laws. Gravity. Yeah, so gravity. Gravity. That is a force of attraction between every particle of matter in the universe and every other particle of matter in the universe. Near the surface of the Earth, the force of gravity on an object is called the object's weight. And that is equal to the object's mass times the acceleration of gravity, which is about 10 meters per second squared. And this whole thing is written much nicer like this, mg. So weight is equal to mg. It's the mass of the object times, we're going to use 10 meters per second squared, the acceleration of gravity. And for an object near the surface of the Earth, that force is always there unless it says ignore gravity. So, problems involving gravity. Here's a problem. All right. We're going to throw something here across the room. Oh no, you might think, oh no, projectiles, what? I thought these were about gravity. Yeah, they are about gravity. So, when this object is at the very highest position, what is the force of gravity acting on this object? It's a ball. And furthermore, that ball has a mass of 2 kilograms. So what is the force of gravity acting on this thing? Well, it's mg, and it points straight down. So the force of gravity on this ball at its highest position is 2 kilograms times 10 meters per second squared. So 2 times 10 is 20. And a kilogram times a meter per second squared is a newton. So yeah, the object's weight is 20 newtons. What is the object's weight right here? Well, it's 20 newtons. What is the object's weight before you throw it? It's 20 newtons. That force is constant. It doesn't change. It sticks with that object the entire time it's around, right? As long as it's near the Earth. There we go. 20 newtons. Okay. It's not 0. It's 20 newtons, regardless of where this ball is. So, problem number 2. Let's launch a rocket up in the air. So, we've talked about rockets. I just like drawing rockets. And then it's got this thrust coming out of it. And again, this thrust ejecting downward, producing a force upward, is related to Newton's third law, which we'll get into in much more detail in the coming week here. But for now, there's a thrust force acting on the rocket, and that force is upward. And let's say that this thrust force is 50 newtons. And let's say, furthermore, that this rocket has a mass of 2 kilograms. All right. And so then, what is the rocket's acceleration going to be? Given that you ignite the engine and all that gas coming out of the engine exerts an upward force on the rocket of 50 newtons. So what is the acceleration of the rocket? How much speed does it gain every second that the engine is burning? So all I need to draw the other forces acting on the rocket. There's just one other here in consideration, and that's the weight of the rocket, which is mg. So for a rocket that has a mass of 2 kilograms, that is 2 kilograms times 10 meters per second squared. So that's 20 newtons. Okay, I have 2 forces now, and so I'm going to write down Newton's second law. In this problem, I'm going to call up the positive direction. So net force equals mass times acceleration. And here the net force is going to be 50 newtons minus the downwards force here, 20 newtons, is equal to 2 kilograms times A. So on the left, 50 minus 20 is 30. So 30 newtons is equal to 2 kilograms times A. So now divide both sides by 2 kilograms. And so 30 divided by 2 is 15. And a newton divided by a kilogram, believe it or not, is a meter per second squared. And here the 2 over 2, that cancels out and just becomes 1. And so there you go. This rocket is going to have an acceleration of 15 meters per second per second. So every second that engine burns, it gains speed. It gains 15 meters per second of speed every second. Okay, problem number 3. Ooh, here we go. Okay, elevator. So you're inside of an elevator. That's a big box. All right, and I don't know, the elevator might have a cable pulling it up. It might have a piston underneath it pulling it upwards. I don't know. And you're standing here on the floor of the elevator. And that elevator has an acceleration of 1 meter per second squared upward. So let's say the elevator starts at rest. It's got to gain speed to get going. It's not going to gain speed for very long. It's going to reach a maximum speed and then just cruise up with constant speed. So while it's accelerating, it's going to gain a meter per second every second that cable is pulling it upward, right? And let's say that this person has a mass of 50 kilograms. And so the question is, what is lifting the person up? So what force is lifting, because that person is moving up. So, well, it can't be gravity. Gravity is definitely acting on that person. I'm going to draw that gravitational force. And that's mg. We could figure that right away here. It's going to be 50 kilograms times 10 meters per second squared. 50 times 10 is 500. So the weight of that person is 500 newtons, and that force acts down. But if that person is accelerating up, something's got to be accelerating them. There has to be a force acting on them that's not gravity. And, well, what about this cable right here? Yeah, no, that's not touching the person. All right, there's got to be something touching the person, accelerating them upward. It's the floor of the elevator. It's the bottom of the elevator that your feet are on. That's exerting an upward force on you. That force has a name. It's called the normal force. So I'm just going to draw it right here. So N for normal force, Normal. That just means it's a math way of saying it's a force perpendicular to the floor. It's at right angles to the floor. So now we're going to write down Newton's second law and figure out how large that normal force is. So I'm going to write, well, of course, it's net force equals ma. It's the same equation for every one of these problems. There's not a separate equation for whether it's a rocket. There's not a separate equation for a car with friction. There's not a separate equation for a rope tied to a ball. It's all the same equation. Its net force is ma. And then you got to draw this picture, I'm telling you, and draw these little arrows here. So we're going to call up positive. And the two forces in this case are N and mg. So I'm going to write N minus mg equals ma. Okay, and now we could put numbers here if you want to. So N minus mg is 500 newtons is equal to, so the mass of this person is 50 kilograms, that's m. The acceleration is 1 meter per second squared. So 50 kilograms times 1 meter per second squared. So 50 times 1 is 50. And the kilogram times a meter per second squared is a newton. I'm also going to add 500 to both sides to get rid of that. And so I've got N is equal to 50 plus 500 newtons. So yeah, N is equal to 550 newtons. Problem done. In other words, you actually feel heavier when that elevator is accelerating, when it's lifting up off the ground. You may have noticed that if you're in an elevator. You can definitely feel it when it takes off. You can feel it when it slows down. You can't feel it when it's cruising with a constant speed. But for a moment there, your sensation of weight increases. The floor is you haven't really gained any weight, but what gives you your sensation of weight is the floor pushing up on you. And that force increases in order for you to accelerate upward. So, problem done. And that's good for now. Okay, 3 problems. You should work these problems and then rework them. And then you should rework them multiple times. Got it? Okay.